Okay. Now, as many of you guys hopefully remember, ATP is one of the two or three primary storehouses for the energy that cells are going out of their way to extract from their environment or from the things that they eat, um, that they can then use to do all the important stuff that creates life, right? So ATP is right at the very core of essential energy currency in a living cell. The question is why? Why is ATP such a great place to store energy, the free energy, um, in a chemical form that cells need to live, right? So another way to ask this, right, is if you think about um, in a thermodynamic sense, right, you think about a reaction coordinate, and this is of course energy, and over here we have ATP, and over here we have ADP plus inorganic phosphate. We know that we have this large free energy change going from ATP to ADP. That standard state, right? That's minus 31 kilojoules per mole. Okay, fine. The question is why? What is it about ATP that makes it have such a large hydrolysis or uh, free energy of releasing that inorganic phosphate, right? Okay, there are a whole bunch of reasons for this, right? So we need to start at the beginning. For one, um, think about it. Think about that basic reaction. We're talking about going from ATP to ADP plus inorganic phosphate. And you just think about it again. Think about this in terms of, think about energetics, in terms of the Gibbs free energy. Delta G naught prime equals delta H naught prime minus T delta S naught prime. Just right out of the gate. If you think about that reaction as I've written it down there, ATP, what's happening? You've taken one molecule and you've made two, right? So you have one molecule with its associated degrees of freedom and vibration and rotation and hydration and all that kind of stuff. And now I've made two, just from a simple molecularity point of view, right? As we take ATP and make ATP, make ADP and inorganic phosphate, we've got more molecules. Right? From an entropic point of view, that's good. That's delta S going up, right? So just the molecularity of that hydrolysis reaction alone increases the entropy. So, okay, so that's a favorable term. All right. What's something else you know maybe about ATP, right? That inorganic phosphate, if you take inorganic phosphate and you write that out, right, it looks something like this, right? That's the way sort of, standard sort of chemical notation would be for inorganic phosphate, right? You just look at that molecule, something else can happen there, right? Think about this molecule. I can take these electrons, I can move those over there, these would go up here, right? Which means this guy also has another resonance state. I just move that oxygen double bond over here, right? But do I have to stop there? Is that it? No, hopefully you guys remember. No, I can do that again. I can go here, then I can do that there, which means I can write this. This guy is here. I got there, O minus, here, O minus. And I got another one, right? Which means inorganic phosphate is stabilized by four equivalent resonance states. They're energetically equivalent. That phosphoester bond, right? If we had, oh geez, what is that thing? That phosphoester bond, right? You can't do that, right? You've got a few resonance states over here, right? You can move this guy over and do this, right? You can move around, but that oxygen, right, that's tied up in that phosphodiester bond, it doesn't have access, right? So again, you get an additional resonance state here, which again means that entropy goes up, right? So hydrolysis is entropically favorable, both from a molecularity point of view, from a resonance point of view of that inorganic phosphate. Okay, that's good. Anything else you think about it, right? And if you look at that phosphoester bond, phosphodiester bond that I just drew out there, what's something else you notice about this guy? Let me make this a little more explicit here, right? Notice something? And I'm gonna just highlight it. D, D, D. That's a lot of negative charge, right? That's a lot of negative charge crammed up. And of course, there's another phosphate group, if it's ATP, I'm gonna be explicit about this, all right? We of course have another phosphate group over here. Um, Adenine, right? So here's another one, right? That's a lot of negative charge crammed onto the end of this molecule. And even with all the, um, you know, counter ion shielding you would get by collecting up cations, all that, you don't completely in any way negate all that negative charge, right? So there is a very, very favorable exothermic or negative delta H, right? Very favorable enthalpic driving force to split that phosphoester bond, right? Right? And now separate that concentrated negative charge into two molecules that can now go about their business, right? That is enthalpically quite favorable, right? But it's even better than that. Notice something. We took this phosphodiester here. Let me do that a slightly different way. We took that phosphodiester bond here, right? And what do we generate? We generated two acid oxygen groups in water. What do you think those guys are going to do out in water, right? Water molecules flying around. It's not so easy for water molecules to get down in here, right, and interact with that oxygen, right? It's tied up in this phosphodiester bond. You've got other oxygens all around in here. You're going to have some ability of water molecules to sort of hydrogen bond a bit, right, with the oxygen in that phosphoester bond, right? But it's going to be limited, right? Because you've got a lot of other stuff going on around here. These guys are crammed up near each other. There's not a whole lot of space. Van der Waals repulsion, blah, blah, blah. But look, what's going on here, right? You've got this now acid oxygen exposed when you hydrolyze that bond. Water molecules can happily snuggle up to these guys, right? And hydrogen bond with those acid oxygens beautifully, right? Interact with the negative charge of the dipole, hydrogen bond with it. This sort of hydration is of those acid oxygens, once they're exposed, is associated with an additional favorable enthalpic term, right? Another nice exothermic negative change in the enthalpy, right? Okay, so that's another good sort of reason to take that ATP and split it into ADP and inorganic phosphate, because you create those two new acid oxygen groups that are wonderfully happy in water and make all these great interactions with the solvent. Okay, so that's sort of a fourth reason for why the free energy is so favorable. There's another reason, fifth one. I kind of introduced this to you guys before a little bit. Remember, in water, in buffered solution, what else happens when you you clip that phosphoester bond, right? To create ADP, right? Plus HPO4, 2 minus, right? chemical balance, you release a proton. That hydrolysis reaction releases a proton, right? The release of that proton, right, in just water would eventually shift the pH so much that the hydrolysis reaction would stop happening, right? You'd inhibit it. But in buffered solution, we know that's not true. We know we can write out the free energy for this overall process as equal, again, we did this just a minute ago, delta G naught plus RT log of, ADP plus inorganic phosphate over the concentration of ATP. But we've got this other term over here, right? Remember, we did this early when we talked about standard state, biochemist standard state, where protons are not really a variable, right? Because if we're at pH 7, there's this additional term, 10 to the minus 7th, right? Log of 10 to the minus 7th, right? And this sort of, again, comes back to, we've been combining that to create this delta G naught prime term, okay? So at neutral pH, the fact that the buffered solution is going to soak up those protons is going to help pull that hydrolysis reaction in the direction of ADP and inorganic phosphate, because you're basically soaking up one of the products of the reaction, right? So again, you put all of this together at neutral pH, buffered neutral pH, under sort of physiologic conditions, the actual ATP hydrolysis free energy for ATP, right, is actually closer to about 50 kilojoules per mole, versus that standard state free energy, which is closer to something like minus 31 kilojoules per mole, right? You get an additional kick of almost 20 kilojoules per mole for the hydrolysis free energy of ATP under cellular conditions, right? Which is great, all right? That means all this great energy you can do stuff with. Think about that for just a second. Oops, minus. This awesome place to put energy, ATP, right? It's unstable by a lot under cellular conditions. Why is that a good place to put the energy you want to use, right? I mean, it doesn't want to be there. It's unstable. You have a massive driving force to take that ATP and turn it into ADP and inorganic phosphate. Why would you do that, right? Just from an energetic point of view, if you wanted to keep your energy stable, you keep your energy stored, why would you do that? Okay, let's go back to our diagram here. I'll draw this out again. Remember, here's our reaction coordinate again. It's our energy. Here's our ATP. Over here is ADP plus inorganic phosphate. Why on earth would you put ATP or store all this energy you need in a molecule that is so fundamentally unstable? Minus under cellular conditions, minus 50 kilojoules per mole. Why do that? It's thermodynamically unstable, right? Well, to begin with, that's what you want, right? Think about my cocked spring analogy I've used before. I'm talking about hemoglobin, right? The fact that ATP is unstable means we can get at that energy. It's like having the power on in the wall that you want to plug your computer into, right? The power company is not cranking up the potential energy in that circuit. You don't have anything to work with. ATP being thermodynamically unstable is the same thing. That's your potential energy. That's the energy you want to get at. You want it to be thermodynamically unstable so you can tap it when you need to, right? That's your potential, your stored potential. But the reason ATP is such a great place to put it is even though, and on purpose, it is thermodynamically unstable, hydrolysis of ATP is kinetically unfavorable, which means ATP by virtue, but ATP is thermodynamically unstable, but kinetically stable, which means then that the transition state for spontaneous hydrolysis of ATP is large and unfavorable, right? So that delta G naught prime double dagger, delta G naught double dagger, is large, positive, and unfavorable, which is perfect, right? That's exactly the situation. There's your cocked spring, right? It's pulled back, we stored the potential energy that held back, stabilized by this unfavorable kinetic barrier. And now all we've got to do is figure out some way to release it, right? And remember, that's exactly what enzymes are going to do, right? Is drop that transition state free energy barrier, right? That's flipping the switch on the wall to let the power flow. Okay, but it's worth thinking about. You know, that's the big picture. That's the idea. It's exactly what you want. It's a great place to store energy, right? It's there. The potential's there. Not going to leak out very efficiently, very easily, because the transition state barrier is large and unfavorable. But you know, we know how to turn the switch on. We can get at it when we need to, and we do it fast, right? But it's worth thinking about why do you think that transition state free energy barrier is so large, right? What makes that transition state for hydrolysis so unfavorable? Well, again, if you think about that terminal phosphoester bond here, right? Let me just write this a different way. This would be ADP, right? And then there's our terminal phosphate group in that terminal phosphodiester. That phosphate group here is not a very good electrophile, right? I mean, it's got all this other oxygen on it, right? And it's not really in the mood by itself to soak up more electrons, right? And what we have to do, the transition state we're going to have to get to for this molecule is going to be to go, well, I got to take ADP, here's we are again, here's our phosphate group, and we've got to have, essentially, if we're going to hydrolyze, a hydroxyl equivalent attack that phosphate group, right? To create a transition state that's going to look something like this. O minus, O minus, O minus. There's our hydroxyl, right? There's our transition state. You look at that. I mean, look at all that negative charge. I mean, look at this thing, right? And this sucker is just packed up with negative charge, all clustered around this phosphate. That's a lot of a negative charge in a very, very small spot. You can now hopefully understand why getting that to happen is not going to be energetically a very favorable thing to do. The transition state is very high in energy. This is extremely energetically unfavorable. And what you got to do is figure out a way, or what an enzyme's got to do is figure out a way to make that transition state much more favorable by dropping the unfavorability of that transition state. And that's what all these enzymes that are going to use ATP are going to do. And there are lots of ways they do it. It involves, in many cases, some really important electrostatic catalysis, often involving metals like magnesium and potassium that help screen some of this charge. We can then, if we understand how these enzymes work, understand how they go about getting access to that free energy and getting these unfavorable reactions that we need to run to get them to go, right? Okay.